patient.
Yeah, yeah, no
So
problem. You can just
that's the issue. Otherwise,
yeah,
there will be nothing.
yeah. You can just tell me, and I'll just pause the recording or whatever, and yeah, then uh, you can continue on with your stuff. So yeah,
Okay.
pretty cool. All right. So, mm, hmm. So I'm in full screen. Yep. Mm. All right. Hey everyone, welcome to another episode of the Wimper Podcast. A long time it has been since I've uploaded anything. I've been a bit busy and at the same time have been overwhelmed with a lot of other stuff in contrast to the podcast. But I guess next year we'll be having a lot more of this stuff since it's going to be about 3 or 4 months of time before I start my next term of higher education. So, yeah, now, today I have Dr. Sayantan Choudhury, who is a physicist. And yep, uh, Dr. Sayantan Choudhury, it would be great if you could uh, introduce yourself to the audience. And yep, welcome to the Wimper podcast as well.
So hi to all. I'm Sayantan Choudhury. I'm an assistant professor at Center for Cosmology and Science Popularization, and it is in the name of Professor Thanu Padmanabhan, the late Professor Thanu Padmanabhan. It is situated at Delhi NCR,
Mm-hmm,
Gurgaon. Um, my prime research area is theoretical cosmology, quantum information theory, quantum gravity, and quantum field theory. So this is my prime research area. In quantum gravity, mostly the ADA safety and string theory.
mm-hmm,
Uh, yeah, and yeah, like I did my uh, bachelor's, master's, including PhD from India. So I did my PhD from Indian Statistical Institute, Kolkata.
mm-hmm,
Then I was a postdoc at Tata Institute of Fundamental Research, Mumbai,
mm-hmm,
and
mm-hmm,
I was a postdoc at IUCAA, Max Planck Institute for Gravitational Physics, Potsdam. Then I had several positions in various other institutes like NISER Bhubaneswar,
mm-hmm,
IOP Bhubaneswar,
mm-hmm,
International Center for Theoretical Sciences, Tata Institute of Fundamental Research, Bangalore Center. And after that, I have joined here as an assistant professor in the year 2022 August.
mm-hmm, mm-hmm.
And since then, I am continuing as an assistant professor here.
Pretty
Yeah.
cool, pretty vast set of expertise and experiences that Dr. Sayantan has. And I hope this conversation is also going to be turning out to be quite fruitful for everyone listening and for me as well as Dr. Sayantan. So, Dr. Sayantan, I have a few questions before I start. So, now that we know that you've studied a lot of physics and that you teach a lot of physics, one of the major questions that I would certainly ask as a career option in physics for students. So, I mean, a lot of students believe that uh, a B Tech over BSc is better. You know, and that is true for in some sense, unless and until you're only targeting the job market. But however, there are few exceptions to the same. A lot of physics majors do very well in the job markets as well, and so if you could shed some light upon on this, you can say paradigm over what to choose and what not to choose, not just based upon your interests, but also what the market is trying to analyze over yourself. So, could you guide the students over should they study physics or as a major, or should they just go for core engineering or something like that?
Sure, sure. It's a very nice question and very relevant question from the present perspective, present situation, whatever going on in
Mm-hmm.
the job market. Um, If you want to take uh, physics as a career, so in
Mhm.
that case I would suggest to do the bachelor's major, means like which is BSc honors. That's a better option than the BTech. uh, it's, yeah, I believe that the basic courses it's covered. No, I'm not saying that BTech course is bad. In some of the places like IIT Kanpur, IIT Madras, those places basically doing it very greatly. Their curriculum is really great, and a good professors are teaching. You will get a good uh, overall knowledge during your BTech, which will be helpful to get in the PhD, etc. If you want to do in India and outside, both of them uh, can be done from BTech as well. But I believe if you want to really strengthen your basics, good universities, even in good institutes uh, in India, they are doing very great. Means like I have to say, ISERS, NISER, they are doing exceptionally good in their BSMS program, which is like the joint bachelor's master's program. Okay, I believe this type of training has to be needed. It's necessarily needed to get into this PhD program. And during PhD, you have to learn new things. But during learning, it has to be assured all the basics you need uh, to know all these things already you have studied before. In BTech courses, mostly the courses are oriented towards the technological side. Okay, I'm not saying all the courses are bad, some of them are good, but you need to take more courses to get into their curriculum in this BTech curriculum. Like you can opt some quantum field theory courses in IITs, etc. But you can't take those courses as a major course in the part of your curriculum. So you can't, if some professor is teaching quantum field theory course, you can take that. You can attend those courses. That's why I have took the name of IIT Kanpur, IIT Madras, particularly. They have very good teacher in the physics departments as well. They used to take parallel courses. So even if you are a BTech student from these places, you can able to get into all those courses and get into
Mhm.
all these new subjects. But for me, if you are really interested to know
Mhm.
what is exactly going on in the deep root level,
Mhm.
better better to go for BSc major,
Mhm.
which we call honors.
Mhm.
Okay, physics honors.
Mhm.
And good colleges, good universities, including ISERS,
Mhm.
um, they have their BSMS program,
Right.
and that's really good.
Mhm.
I have to.
So what you're saying is, mostly for students who do their due diligence before trying to get into any college or university. Um,
Mm-hmm.
but like for example, from my experience, what I've seen so far, as at least for undergrad students or students who are getting into bachelor's programs, they barely do their due diligence or any form of research regarding what they want or where they want to go. For example, even in the IITs, most students try to perceive an IIT with being better or worse in comparison by the salaries that they are
No, no, I agree with your statement,
yeah.
but I'm talking about, I'm not
Mhm.
talking about all the students, those who are
Mhm.
studying in bachelor's major curriculum.
Mhm.
I'm saying the people, if you are really interested in physics,
Mhm.
there are good students as well. They are very much
No, no,
interested.
not
They are,
comparing about the students. This question is different. What I'm trying to propose over here is, there's a mistake that students do a lot of times. Okay, what you're saying is entirely correct. Obviously, you know what you're talking about,
Hmm.
and what these students most of the times do, that they don't do their particular research over which universities they want to get into. For example,
Oh, you
yeah,
just ask saying that randomly they just get into
yeah,
somewhere
that's
and they stuck into somewhere. This is very
yeah,
bad. This
yeah.
is very bad.
This is, and I see this as a very common thing. For example, if you go to all the IITs and all the top institutes in the country, so IIT Kanpur or IIT Kharagpur, these are named as public research universities, whereas IIT
Hmm.
Bombay is not mentioned to be a public research university. It is like an all-round university. It has all of the things possible if you want tech or you want research. However, some universities are more dedicated towards research. Now, this is a very basic idea that I am aware of. However, most students do not even try
Most
to,
of them
most,
are
yeah, they don't even try to gather this kind of information. They mostly judge IITs or any institute, in fact, on the basis of the
yeah,
salaries that are offered
maybe,
post
maybe,
graduation.
maybe, maybe the salaries, maybe the world rank, all
Yes,
those things
yes. QS World
usually.
rankings and all of that.
Yeah,
So,
yeah, yeah.
yep. So, I would like to ask you why this happens, and second of all, how could students get better at researching where they want to get into?
That's a very good question. Unfortunately, we are living in a country where we don't have any kind of encouragement to do good research in theoretical as well as in experimental areas. Okay, in abroad, in most of the countries, if you go roam around, you will see they provide a sufficient number of help from the government side as well as from the public sector as well. Here to get such help, any kind of thing from outside, you have to do a lot, and after doing a lot you may not get into anything at the end of the day. uh, it's very bad. And also, like, the important thing is the awareness. Since there is no encouragement,
Mm-hmm.
the awareness is very poor. Means, like, people are not, most of the, you already have mentioned, a lot of people don't know that which IITs are good in research, which IITs are not good. So this uh, differentiation, this discriminations, this knowledge, even people are not aware of, because there is no awareness
Mm-hmm.
itself. um, Most of the IITs, they don't tell the truth
Mm-hmm.
or isers what is their flaw, what is the problem. They just want to, it's a kind of a selling story. Means they want to sell whatever they have, but they don't tell people that they don't, whatever they don't have.
Right.
Okay, now that's the bad part, because of that a lot of people uh, uh, not get the proper information. And yeah, like, I believe this is the reason.
Mm-hmm.
Mostly there is no encouragement from the government sector,
Mm-hmm.
in and as well as in the public sector.
Right.
Mostly I have to say,
Mm-hmm.
the from the government sector there is no encouragement to do theoretical physics.
Mm-hmm. Mm-hmm. Yeah.
Okay, so, like, if you study theoretical physics, most of the people will tell you, oh, you will not get any job in later.
Yes. Yes.
So you have to choose cleverly something
Mm-hmm.
which will helps you to get job in near future.
Yeah.
Okay. First of all, in India, job market is horrible in academia.
Mm-hmm.
Okay, it's a horrible. After COVID, things get more worst.
Right.
Okay,
Yeah.
and another important thing from the government side, they have included reservation,
Oh yeah.
SC,
Mm-hmm.
ST, SC, ST, EWS.
Mm-hmm.
It is included in the faculty selection as well.
Mm.
Not only,
Oh yeah. Mm.
yeah. So
Mm.
all this, so how you will get into good teachers, good professors if you include this type of policies?
Mm.
Huh? Because these will, the professor selection, faculty selection has to be done in the merit basis.
Right.
Now, if you really want to hire a good person from
Mm-hmm.
the government side, due to having this type of constraints, you can't able to hire. So isn't it kind of a huge constraint coming?
Mm-hmm.
It's a huge constraint. I believe that, and not only that, in other cases like uh, PhD student selection, if you
Mm-hmm.
see, there is also this reservation thing is happening.
Yes, yes, yes.
Okay,
Hmm.
so I'm not saying this is very bad. I'm not against to giving chance to the SC, ST or OBC or EWS candidates,
Mm-hmm.
but I'm strict against going beyond the merit,
Mm-hmm.
which is very, very harmful for research.
Mm-hmm. Mm-hmm. So, um, so you're saying particularly that students should see both the good and the bad of a university, which or college, whatever they want to get into, that they don't usually do, and then you criticize that the very job market for academia in India is horrible. Now, at the same time, in the past couple of years after COVID, we've seen this. I don't know how much you follow politics. Even I don't not do not follow much. But if you see on the geopolitical strata, pro-India conversations have become a norm. You know, like people believe more in a better future for India. Like Indians particularly are very optimistic about the future of India in every other way possible. So, do you think there's a reason that this irrationality of only seeing the positive side of things and not seeing the negative or the flaws so that one can improve upon them is one of the reasons why not just I'm not just talking about politically, but also one of the reasons why the job market has become this way, that only particular type of people, like we have a great IT industry, right? We have great software engineers. The CEO of Google is Indian and all of that, but we don't have a great manufacturing sector. So and and all of these things result into statistical data saying that 60% of the good students who are actually at good universities, IITs and all of that, they don't go into the job markets that are related to their core subject that is studied at the institute. So what do you think this bias presents to us?
It's a very good question. It's a very difficult question as well because, um, yeah, like some of the political reasons are
Mm-hmm.
there.
Mm-hmm.
Means one of the thing is government's perspective is if I spend money for you, what you will give me in
Right,
return.
right, right.
Means they are actually. I'm not blaming the government,
Mm-hmm.
but government is also pissed off with having a lot of bad incidents from different types of institutes and universities. People misuse the money in different contexts. Now government is asking that we are providing so many funds to all of you to do good research. What is the outcome? Why you are not getting position at Nobel Prize? Why you are not getting good recognition outside India? What happened exactly? These days you have a lot of uh, facilities coming from government. You have a lot of fund from the institutes as well as from the government side, but why you are not capable to do anything at all? That's why government is asking all the research institutes to uh, include teaching as a mandatory curriculum in their uh, administrative thing, because without teaching a researcher,
Hmm.
I also believe that
So you're saying
without,
that the student should also learn to teach?
not student but at least the
The
professors,
professor
the
himself, yeah, cool. Yeah.
yeah, the researcher. If you
Hmm.
go to the most of the research institutes 5 years ago, I'm just talking about,
Right.
most of the research professors were was not teaching. I'm
Hmm.
not talking about TIFR, I'm not talking about IUCAA, I'm not talking about big research institutes,
Hmm.
but I'm talking about in general,
Right.
because that was not mandatory.
Hmm.
Now government putting this constraint that you have to teach,
Hmm.
and whatever salary you will get at the end of the month because of that teaching, not for your research.
Hmm.
Once you will give us that amount of output from your research, then we will rethink whatever
Mhm.
uh, fun cut we did.
Mhm.
Maybe we will restore all of these things later. But for now, prepare students, make the society. That's your main job. So I believe that is not a very bad thing.
Mhm. Yeah.
So without teaching, doing research, I believe that doesn't mean actually anything.
Mhm.
Uh, so that's very important thing. And yeah, so this is basically the political side. So government is very much
Mhm.
right now uh, interested to see what is the outcome. But all of the cases they are not they are not taking the correct steps, are not promoting the government. This is not a
Mhm.
kind of government
Yeah.
rally. But I'm saying that all the decisions,
Mhm.
whatever we are seeing right now,
Mhm.
it's somewhat we did before, some bad things.
Mhm.
The impact right now is coming this way.
Mhm. All right. So okay, this was about academia and all of that, which was just out of curiosity. This was none of this was in the script. Now, I would like to ask a few questions over what I have on physics and quantum gravity and quantum field theory. Uh, that are some of the topics that you're really interested in and you really like to talk about. So, I have this question over here where it says quantum gravity, as to what I personally got was that it's quite different from the way it works from the classical definition of gravity, right? So, and it creates a brilliant argument between physicists for the sake of what is true versus what is perceived to be true. And I want to know that what do you think has been the best argument that supports quantum gravity and its mechanics over the classical arguments, or do you rather try to find harmony between the two?
Yeah. Uh, so classical gravity and quantum gravity, they are
Mhm.
not same, obviously, but
Mhm.
classical limit of the quantum gravity has to be the classical gravity. And what is the classical limit of the quantum
Quantum
gravity?
gravity. Mhm.
Which is basically the Planck's constant has to be taken zero. This
Okay.
is the classical limit.
Mhm.
And what do you mean by quantum gravity? Gravity is obviously classical.
Mhm.
Gravity is basically the kind of an uh, outcome of uh, the space-time,
Mhm.
space-time foliation, space-time curvature,
Mhm.
everything you can write in terms of something called distance.
Mhm.
And this distance is characterized by something called metric of the space-time.
Mhm.
Metric is basically the classical object. And in terms of metric, you define the curvature of the space-time and other parameters. And using that, you can quantify the local and global space-time in which you want to do the calculation. Now, quantum gravity is this class. They are trying to quantize this classical gravity,
Mhm.
classical object. It's called metric.
Mhm. Mhm.
Okay. Uh, what people do actually, this metric is a very fundamental object in general theory of relativity, and this metric basically decomposed into various fundamental parts. One
Mhm.
is called scalar degrees of freedom, which has spin 0.
Mhm.
Another one is vector degrees of freedom, which has a spin 1.
Mhm.
And third object, which is extremely important, which is graviton. People call it graviton mostly, but in uh, usual language, what it's commonly known, it's called gravitational waves.
Right. Yeah.
Uh, now
So they
this,
say that graviton produce gravitational waves or something like that.
yeah, yeah,
Yeah.
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 But we call it graviton once we quantize it.
Mhm.
Okay. The now the point is it's a very difficult. People are
Mhm.
trying to do this quantization for very long time,
Mhm.
and people failed
Mhm.
because gravity is not, particularly the Einstein gravity.
Mhm.
Okay, Einstein classical theory of gravity is not protected from quantum corrections in the high energies.
Hmm.
Okay,
Hmm.
so there is a infinite corrections, means infinite number of term you can able to add.
Hmm.
Okay,
Hmm.
and it's basically diverging series type of, means you can't able to end that series.
Hmm. Hmm.
That's why this series is not complete.
Right.
And this language in quantum field theory, people call it not UV complete.
Hmm. Hmm.
Okay.
Hmm.
UV is the ultraviolet. Okay.
Right. Right.
Yeah. So this type of theory is not UV complete.
Hmm.
Then actually two school of thoughts came. I hope you know that. One is called the loop quantum gravity.
Hmm.
Another one is the string theory.
Right.
Okay.
Yep. Yep.
So both of them actually tried to quantize gravity in a
Could you
different.
differentiate between the two for the audience?
Yes, loop quantum gravity is basically, though I'm not an expert, but I can able to tell you the basics. So
Hmm.
they actually discretize the whole space time in terms of the spin networks.
Right.
Okay, SU2, we call it SU2, means special unitary groups. It's
Hmm.
kind of, you just forget about SU2, but it's kind of spin networks.
Hmm.
Okay, this network theory you guys read in this machine learning thing. It's a
Hmm.
kind of neural network type of thing.
Yes. Yes. Hmm.
Hmm,
I'm
it's a
aware.
kind of
Yeah.
mesh type of structure.
Hmm.
They have discretized the whole space time
Hmm.
and quantize each of the box, and then take the sum over all the box in the end.
Hmm. Hmm.
But the
Hmm.
problem with this kind of, this is an extremely good scenario, and this type of scenario was proposed by Professor Abhay Ashtekar from Penn State.
Right.
Pennsylvania State University.
Hmm.
Now, the thing is, this mathematical framework is very good,
Hmm.
very elegant. But the problem is, after quantizing the thing, the basic objects like entropy, so loop quantum gravity can't able to produce the correct signature of black hole entropy
Hmm.
uh, for Hawking evaporation,
Hmm. Hmm.
Hawking radiation.
Right.
Okay,
Hmm.
it can't able to produce the correct uh, signature of the entropy.
Hmm. Hmm.
On the other hand, um, in string theory, the idea starts with Nambu Goto,
Uh-huh.
uh, and then uh, they actually quantize the gravity in a very different way. The theory actually was written in two dimensions.
Hmm.
Any means in four dimensional theory is basically parameterized in terms of two dimension,
Hmm.
and there people after quantization could able to produce the correct signature of the entropy that I was talking about.
Right.
Okay, this is one of the differences between loop quantum gravity and string theory predictions. There are
Hmm.
many more. Means I can able to tell you many more.
Hmm.
Uh, in the cosmological perspective,
Hmm.
uh, we believe that our universe is one of the
Hmm.
minimas of infinite number of minimas, which is called multiverse.
Hmm.
Okay, so you may have
Oh yeah.
10 to the power 10,000 of universes,
Yeah. Yeah.
and you are sitting in one of them.
Hmm.
Who will give you this type of solutions? String theory can able to give you this type of solution, multiverse solution.
Right.
And from the cosmological
So if
perspective,
you
you.
okay, sorry to interrupt you. So if we
Hmm,
have to do such complex calculations, where you said that 10 to the power 10,000 possible
hmm,
universes, you
hmm,
said, and this is something that string theory proposes that it can be done.
hmm.
And so, what does it propose
No,
by?
not it can be done. They have done it.
Okay, they have done it. Yeah. So
They have done.
what did they use? What method or what like I don't know if it would go too deep into it so that our audience may not
No,
understand.
I can understand. At least I
Yeah.
can tell if somebody is interested.
Mm-hmm.
So the basic knowledges of general theory of relativity,
Mm-hmm.
basic knowledge of differential geometry,
Uh-huh.
quantum field theory,
Mm-hmm.
of flat space-time and curved space-time
Mm-hmm.
and conformal field theory.
Mm-hmm.
And not last but not the least, classical field theory. So these subjects, whatever I have mentioned right now,
Mm-hmm.
these are the building blocks.
Mm-hmm.
You have asked me that what kind of, so what is the origin of this type of complicated calculations?
Yes. Yes.
These are the things you have to at least read
Mm-hmm.
to get into this calculation.
Mm-hmm.
Now, I'm not actually demotivating everyone. I'm trying to give answer to everyone so that people can go to home or look at the internet and search for all these things and
Yeah. Yeah.
jump on. Yeah, so I'm
So
trying to motivate.
I'm aware that the mathematics required for doing string theory is a lot more complex than other theories in general. Is it true?
I can't. Yeah, if here I don't want to give you a politically correct answer. Rather, I will
Mm-hmm.
give you the truth.
Mm-hmm.
Yes, I believe you need to know mathematics very well
Mm-hmm.
in the deeper level
Mm-hmm.
to get into these subjects like
Mm-hmm.
string theory.
Mm-hmm.
Okay, even in loop quantum gravity also, like you need
Mm-hmm.
to have a sufficient knowledge.
Mm-hmm. 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 Um. Okay. What's what's something that fascinates you the most about cosmology or space science in general?
Most important part in the present day cosmology, you can verify everything.
Okay.
Whatever thing you propose from theories
Mm-hmm.
is just not vague.
Mm-hmm.
There are lots of data, lots of observation is going on,
Mm-hmm.
and you can actually confront your theory with the observation.
Mm-hmm.
Now, if you give something which can able to directly explain whatever you see in the sky,
Right.
that would
Right.
be that would be a miracle. Means like it's kind of an excellent thing to do,
Right.
and that actually gives you kind of a satisfaction as well because your theory explains the nature.
Mm-hmm. Mm-hmm.
So I believe in that way cosmology is kind of an excellent subject to do
Mm-hmm.
research for future. And cosmology basically is made up of general theory of relativity,
Mm-hmm.
classical field theory,
Mm-hmm.
quantum field theory, maybe string theory. These subjects, if you want to be a theoretical cosmologist, you should know all these subjects up to a
Mm-hmm.
certain level.
Mm-hmm. Mm-hmm.
Then you can propose some good theories, you
Mm-hmm.
can propose some new ideas, you
Mm-hmm.
can play with that ideas
Mm-hmm.
and look for some solution, and in the end you can try to see that your propositions, your solution exactly matches with whatever you see or not.
Right. Yeah, maybe I mean it's the method of scientific research in cosmology that you're talking
Yeah,
about.
and also you do a different thing. It's basically it's called top-down approach. Means you have a theory, you
Yeah.
try to propose the theory, and then try to see how it works with the observation.
Mm-hmm.
Sometimes people do in the other way around as well. Like
Mm-hmm.
having a observation, people
Mm-hmm.
try to reconstruct the theory.
Yes, yes.
What is the reconstructed version? People try to see that whether something available in nature is consistent with that reconstruction or not. If it is matching, then people say that, oh, see that already there is a theory exists. I have reconstructed something. It exactly merges with each other. So like
Mm-hmm.
then this reconstruction give you something very meaningful.
Mm-hmm.
Okay.
Mm-hmm. Mm-hmm.
And other theories which can't able to do that, then you can rule out.
Right.
So ruling out is also another important thing which
Mm-hmm.
sometimes researcher don't like.
Mm-hmm.
Another important thing, because if somebody tells you tomorrow that, oh, your model is ruled out, uh, so people usually feel otherwise angry, or people try to tune their parameters so that it can match with something. I don't like that type of attitude. Rather, this is the time This is the era where we need to come up with solutions where to match with the observation you may need to rule out a lot of theories.
Uh-huh. Uh-huh.
Okay, means origin of the universe maybe can explain with thousand number of theories.
Mm-hmm.
Now somebody is asking you which one is the correct one.
Mm-hmm.
Okay, so that solution you have to give.
Mm-hmm.
So this is
Yeah,
the
yeah.
important.
Understandable. Yeah. Um, and then when we use the term quantum, you know, it's very difficult for people to come up with a, a proposition where they are able to make its concepts suitable also in the large world around. Like, because quantum is something that is proposed to be some on the subatomic levels, right? And even further than that, smaller than that, and quarks and all of that. And then they feel like it does not function to the core realities of how our world works on the macro scale. Although that is not true in many ways. Science and physics, whoever has read about it can tell. But yeah, so that does not function in the core atomic or subatomic sizes. And then, can you make it understandable for someone in general what quantum means to someone who would rather try to implicate into the macro world around us?
So quantum is basically related to micro, meaning
Yeah.
okay, microscopic description
Mm-hmm.
of the space time, of the universe, of an atom,
Mm-hmm.
whatever.
Mm-hmm.
Now, if you really don't know what is microscopically going on,
Mm-hmm.
then my question is how you can able to construct the macroscopic structure,
Mm-hmm.
because macroscopic structure can be divided into infinite number of microscopic structure.
Mm-hmm.
So quantum physics actually helps you to understand each of the microscopic structure. May not be the each of the microscopic structures are similar,
Mm-hmm.
but the properties are not different. Okay, uh, if you know behavior of a single microscopic object, then if you take sum over or integrate over the whole ensemble,
Mm-hmm.
means statistical mechanics or statistical physics, we call it ensemble. If
Yeah,
you
yeah.
take an ability over the whole ensemble, then
Mm-hmm.
you can able to get idea of the whole macroscopic picture. So my belief is just like thermodynamics and statistical mechanics.
Mm-hmm.
I can give an analogy.
Mm-hmm.
So thermodynamics is basically the description at the macroscopic level, but statistical mechanics is basically the description in microscopic level. Now, if you don't know what is microscopically going on, then you can't able to construct any theories of thermodynamics even,
Mm-hmm.
because statistical mechanics at large number of
Mm-hmm.
uh, atomic uh, uh,
Sizes,
if
yeah.
you take the large, yeah, if you take the large number of atomic size limit,
Mm-hmm.
then that will actually goes to thermodynamics.
Mm-hmm.
So my point is
Mm-hmm.
you have to know quantum mechanics
To understand the macro world, yeah.
to
Understandable.
know that to know about the classical world.
Yeah, yeah. Yeah.
Okay, so if that description is not
Mm-hmm.
known, you have to construct that
Mm-hmm.
description, and
Mm-hmm.
in the end, you have to take the classical limit in such a way that whatever we see, like Newton's law, galaxy, cluster, etc., etc., everything has to be restored at the end, in the end.
Mm-hmm. Mm-hmm.
But as a theoretical physicist, as a physicist rather, one should know this quantum behavior of the space time very, very minutely.
Mm-hmm. Mm-hmm.
Otherwise you don't know that. People can ask you that, what, like, you see galaxy cluster, you see sun, from where it came.
Mm-hmm.
Okay,
Mm-hmm.
till now whatever we have a theoretical side calculation, we can able to say that okay, these theories are coming from big bang,
Mm-hmm.
inflation,
Mm-hmm.
these that. That's why theory is playing a very important role. And on the other hand, observation. like cosmic microwave background radiation.
Yeah.
Uh,
Yeah.
a lot of experiments are going on,
Mm-hmm.
like Planck satellite.
Yeah.
Uh, the lot of data
Mm-hmm.
people are taking. So
Mm-hmm.
these things are also important so that in the theoretical side, whatever you propose, it
Mm-hmm.
shouldn't be a vague idea.
Mm-hmm. Mm-hmm.
It should match
Mm-hmm.
with whatever we see in the sky.
Mm-hmm.
So my belief that quantum description, understanding this microscopic description of the space-time,
Mm-hmm.
microscopic description of any kind of phenomena is very, very important to
Mm-hmm.
know about what is happening at the macroscopic level classically.
But then, isn't it, arguable over the fact that you said that in order to make one's theory evident enough, you need to support it with some form of observational evidence. Uh,
See, no, no, observational evidence, why I'm talking about physics is a subject which is always believing in experiments.
yeah, yeah.
Okay, we are trying to talking about physics.
Mm-hmm.
Now, if you just for a time being don't think about you are doing physics.
Mm-hmm.
Suppose
Mm-hmm. Mm-hmm.
from the philosophical perspective, you can construct a consistent theory of a space-time, which is string theory.
Right, right.
Philosophical perspective of uh, from the philosophical perspective, loop quantum gravity actually fails in their calculation.
Mm-hmm. Mm-hmm.
But string theory did a very good calculation, it correctly explained everything. But since string theory is appearing at very high energy scale, like Planck scale, 10 to the power 19 GeV, okay, you can't able to verify such theories because you don't have any probe which can go to that high energies. So you try to see the imprint of that high energies at very low scales, like LHC collider, means the collider, Large Hadron Collider,
Yeah.
or maybe some kind of cosmological phenomena, if you can able to see the indirect evidences of string theory.
Mm-hmm.
Okay,
Mm-hmm.
so I am saying that from the philosophical perspective, from the construction perspective, from the mathematically consistent
Mm-hmm.
perspective, you can actually construct such theories. There is no harm at all.
Yeah.
But
The observational evidence doesn't exist for the same.
it's important once you are talking about you are doing physics.
Mm-hmm. Mm-hmm. Yeah.
That's why there are lots of invention happened in
Mm-hmm.
the mathematics, which are like exceptionally good, but those
Mm-hmm.
calculations actually didn't got Nobel Prize because Nobel Prize, I think it's written that has to be tested somewhere.
Yeah. Okay. 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 Mm. I mean, this also correlates quite a lot to the idea. Richard Feynman, he used to propose a lot of times that we don't know how the electron moves because we haven't seen it, but we use maths for the sake of knowing where it will go and how it will be. I think it
Yeah.
very much correlates to this same idea as well. Um, and so, um, as to what I've read, like staying on quantum mechanics, when a particle is in superposition, right now we talked about how it could be in spin and spin zero in the vector and scalar spaces. Um, it is not in either of the states in the case of superposition in the realm of quantum mechanics. It is said, and it's like in every other state possible, all simultaneously. However, I wonder, since I've been reading and diving a lot into the
The
possibilities, which,
reason, the main reason is quantum mechanics talks about probability.
okay, yeah, yep, yep,
You can't quantify something definitely.
yeah, because I mean, mathematically, the magnitude for a possibility is the square of the possibility. I mean, just the mathematical part of it
And
is
it
what I'm,
has,
yes,
I have to, since you have pointed, it has a deeper connection with StatMech as well. Because
uh
in
huh,
StatMech, we usually take the average value,
mm-hmm, mm-hmm,
statistical average value. Here we take something called expectation value.
yeah, okay, okay, okay,
Both of them are actually same actually.
mm-hmm. So I've been reading and diving a lot into the possibilities with quantum computing as a technology. So and what I've read so far in a few research papers, and I've also watched a ton of courses. I've been attending a few as well, live sessions as well at places, and so I've got to know that storage is a particular problem with quantum particles, since they decay from one state to another, because they are staying in one possible position or simultaneously all the time, um, to another in comparatively shorter periods. Like, for example, in classical bits, you can store information for years or for as long as the very device stay in a proper formation and does not decay. And so, I mean, obviously, this is a very hard problem to solve. Nobody has been able to solve this. But what have you learnt about the possibility of storage of information in quantum particles, and how it can be improved? Like, how can we prolong the uh, quantum state particle to stay in one particular form in order for it to have it stored that particular information that we are trying to store in it for a longer period of time?
Yeah, so that's a good question, but uh, yeah, like experimentally, I don't know how to do it because
Yeah, yeah.
this is very difficult thing to do.
Mm-hmm.
Theoretically, there is something called quantum entanglement.
Mm-hmm. Mm-hmm. I'm aware of it.
Quantum entanglement and more refined version of quantum entanglement, which is
Mm-hmm.
called quantum discord.
Okay,
Okay.
explain that, please.
Yeah, yeah.
Yeah.
So this quantum entanglement is basically the entanglement entropy. It's an entropic measure.
Mm-hmm.
Okay. If you have a state which cannot be factorized, which is not factorizable at all,
Mm-hmm.
it is made up of maybe infinite number of degrees of freedom. They are entangled with each other. You can't separate it out.
Mm-hmm.
In such a system, uh, information can be restored for very longer time, provided you have to have huge amount of correlations,
Mm-hmm.
or sometimes people call it long range correlation.
Mm-hmm.
Okay, if this entanglement entropy is non-zero
Right.
for a system, then you can able to preserve the information very long. Means then your quantum correlation exists for very long time. So,
Mm-hmm.
but this is very theoretical. I'm talking about. You can design such setups, but detecting things in the lab, that I really don't know.
Uh-huh.
Because, yeah, that's a very difficult thing also to do.
Mm-hmm. I mean, obviously, there's speculation over the fact that when anybody is trying to conduct any form of quantum research, and especially in the realm of quantum computing, the interaction of particles within the quantum computer with the particles outside the apparatus is the reason why a lot of errors occur, and they are trying to solve it with the help of temperature for the moment, so that they do not reach highest possible entropy in the least possible amount of time. So yeah, I'm aware of some part of it. However, uh, what I think that because a qubit, which is like a quantum bit, can store a lot more information at the same time
No,
than.
that's so to construct the qubit, you have to have an entangled state. That's why I have
Yeah,
told.
yeah. Okay. I mean, okay.
Yeah,
So your definition of entanglement comes from entropy.
the qubit. Yeah.
Uh, and like, for example, okay, tell me this. So for example, for my definition of entanglement is like this, as to what I've learned, that when we know the state of one particular particle, and it's entangled with some other particle, let's say B, with the help of the state, knowing the state of that particular particle A, we can also know the state of that particle B. So this is like the basic idea of quantum
Basic. Yeah,
entanglement,
yeah,
right?
yeah, yeah.
I mean, could you explain how this correlates with entropy?
Yeah, it's basically connected with something called uh, density matrix.
Uh-huh.
Okay. So you have to construct something called, first of all, you need to construct the state.
Mhm. Mhm.
Once you know the state, then you need to, this state is basically made up of, suppose you have A and B and the
Mhm.
2 degrees of freedom and they are entangled with each other.
Mhm. Okay.
Okay. Now, since A and B both are involved, you need to remove one of the informations
Mhm.
to construct an effective description. So
Mhm.
either you will remove A or either you will remove B.
Mhm.
So if you remove A, then you construct a description, effective description of B, and the other way around.
Mhm.
So the effective description of B, this is called reduced description.
Mhm.
This reduced description basically described by something called entanglement entropy.
Uh-huh.
So if you calculate this entanglement entropy, this measure was proposed by Professor von Neumann.
Mhm.
Okay. So it's a basically some formula trace of rho log rho. This rho is your density matrix.
Mhm.
If this quantity is non-zero,
Mhm.
then you are basically dealing with something called mixed state,
Mhm.
where you have A and B, they are mixed with each other, entangled with each other.
Mhm.
If this quantity is zero,
Mhm.
then you can say that this is a pure state. There is no mixing between A and B.
All right.
Now, if this non-zero means, if you are saying this is the mixed state, how much is amount of the entanglement, you can't able to calculate with that. You
Mhm.
have to go more beyond, means like there are lots of other quantum information theoretic measure which
Mhm.
gives you a proper amount of quantification of the information restored in the system. So this is basically the first litmus test,
Mhm.
whether you have a correlation or not.
Mhm.
If this quantity is non-zero, then you go for the other
Mhm.
quantities.
Mhm. Uh-huh. Um. So, like for example, I think a quantum bit or a qubit can store a. I personally think that because of its possibilities of being in so many multiple states at the same time, is
True.
could be a reason. I think it could be a reason why it can store a lot more information than a classical bit, because although although it cannot stay in one state or in many state or in a particular desired state for a very long time, it can store, I guess, a lot more information because it can stay in so many states at the same time. So it's like going back to the previous question, and it feels like we are compromising longevity over storage. And so I think, am I right to think that uh, am I right to think about information or storage of information in this way, or like, do you have something else on your mind?
No, I don't have any something else, but this is a quite a good thing that you have pointed, I
Mm-hmm.
need to say.
Uh-huh.
So quantum beat plays a significant role
Right.
for this storage purpose. But if you think very deeply,
Mm-hmm.
this is very not, it's not very easy from the experimental perspective, but from the
Mm-hmm.
theoretical perspective, you can design the setup like that, whatever I have told.
Mm-hmm. Mm-hmm. Okay. 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 So that's a pretty good thing. I don't know. I mean, uh, but what is then? What is the possibility, over m- uh, like for example, if I'm able to store different information or a lot larger amount of information per qubit, what is the possibility? I mean, obviously we can use the math for the same, uh, but what is the possibility that it will give me the right information almost every time in comparison to a classical qubit, a classical bit, sorry.
Right information.
Yeah.
So that's why I was telling, because
Mm.
just the confirmation that you have a mixed state is not the sufficient enough information.
Yeah, yeah.
You need to go beyond that. There
Mm-hmm.
are lots of, like one of them is the Discord. Discord is basically telling you, even if the entanglement entropy is zero, you can't say that there is no correlation.
Okay.
There are example in, means it's a kind of an exceptional situation.
Uh-huh.
Even entanglement entropy zero gives you quantum
So
correlations.
okay, there's quantum discord. Um, also explain quantum vacuum in many ways? Like, for example, quantum vacuum, I guess, is the idea wherein, a particle emerges with an anti-particle and both of them collapse in
True,
order to,
true, true.
yeah.
No, not necessarily. That's why I'm talking.
Mm-hmm.
First of all, it is important that where you exactly want to calculate this entanglement entropy.
Mm-hmm.
So you need to provide the system.
Mm-hmm.
Now, once you provide the system, in some way, you have to quantize the system as well. And once you quantize, you have to create some particle, you have to destroy some particle. Then the concept of vacuum comes.
Mm-hmm.
And to calculate this entanglement entropy, you need to take the trace over all degrees of freedom. Now, trace over all degrees of freedom can only be done if you know the correct vacuum. Okay. If
Mm-hmm.
you don't know the correct vacuum, you can't do this tracing operation.
Right. Okay. Um. So I guess we're almost moving towards the end, and it's like a lot of people have on their minds, gravity waves to be something not so usual, and are spending as a civilization over researching it to be rather wasteful. And personally, I don't think so, obviously, but I think it is okay personally to burn a few hundred million or $1 billion for the sake of exploration so that it could get us closer to understanding the universe. So, what do you think of organizations putting in so many resources into such research that the general public doesn't find to be interesting as such?
No, but gravitational waves, that's the thing. Probably you have asked me in some
Like,
point
most
of.
people ask, what is the
No,
utility of the same? And
I can
so,
understand your question, but
mm,
some point you have asked me
mm,
that how these things, whatever theoretical physics do,
mm, mm, mm,
it's connected with the real world or something
mm,
like that,
mm, mm.
or
Yes,
from the
yes.
political perspective,
Mm,
or maybe from the government person, why they should you fund or
mm,
something like that.
mm,
This kind of question you have asked.
mm,
The point is gravitational wave. That's why it is important. It not only connects you with the
mm,
fundamental physics,
mm.
but also it basically connects with the real world. Okay,
Right.
if such frequencies can be detected, such frequencies will be useful to use in some other contexts,
Mm,
like in the microwave, in the other frequency ranges, to make a lot of devices. These things can be used.
mm,
That's why people are putting, people means the government and the resources, whatever we have, they're putting a lot of fund to
mm,
do research in this area, because I believe this is the only uh, subject apart from quantum information theory. This
mm,
is the only subject where people are putting huge amount of fund, since it is connected with the real world as well as it is connected with the fundamental deeper level physics.
mm,
So both of the things you can study. Matlab, you can study the real world physics, real world application, direct applications, as well as you can study the origin of the universe.
mm,
So with a single research, kind of this gravitational wave research, you can actually try to get into this, explain not only the theoretical origin of our universe, but also the its utility.
uh-huh, uh-huh. Well,
So maybe it is a myth. People are not, again, I am saying that maybe people are not aware of whatever going on.
mm,
So this is the main reason, is a lot of calculation is going on, lot of things are coming in, but people are not properly informed, and
mm,
that's the reason we need science popularization.
mm, mm,
Science popularization is an important thing, which basically gives you certain and sufficient number of information to get yourself uh, like to know about all these things
mm,
correctly.
mm, mm,
And my belief is they are doing great. This gravitational wave people are doing great at present. So I
mm,
am suggesting my students to do either research quantum information theoretic area, or maybe in this gravitational website.
Mhm, mhm. All right. So yeah, we've reached the end of our conversation. I am out of questions right now. Uh, Dr. Stanton, it would be great if you could uh, give or provide any form of message to our audience here who are listening to the episode towards the end. Um, and it would be great if you could convey something that you wish to share to the rest of the world.
So I want to share my one of my experiences, whatever I have learned. To become a good physicist, theoretical physicist, you have to question yourself each and every moment.
Mm-hmm.
If you don't have any question, then at that point you are gone, completely finished.
Mm-hmm.
Okay, so my whatever understanding, my experience, whatever I have from that, I can say to become a good physicist, good theoretical physicist, you have to ask question each and every time why this is so, why it is happening, what is the motivation,
Mm-hmm.
and then the question comes how.
Yeah.
Okay, and then what is the application. So
Yeah.
these three questions has to be there.
Okay, so it's
Without
the
these
golden
three,
circle idea, I guess, right?
yeah. So
Mm-hmm.
without these three questions, if you don't have such questions in your mind, I
Mm-hmm.
think then a researcher even is incomplete.
Yeah, yeah. So that's a great
So
framework, I guess, for anybody listening who wants to think in ways to develop their curiosity. It's the idea of the golden circle. You can watch videos about it present on YouTube. But if you want to listen about it in a quick, it's like you need to ask, what am I doing, how am I doing it, and why am I doing it? And these are the
true.
three most important questions that you need to ask yourself. And Dr. Sayantan has provided his vast amount of information over various topics that we have talked about today, from academia to quantum field theory, quantum gravity waves, even the political side of things. And I really enjoyed it personally. Uh, and I hope this has been a fruitful conversation for everyone listening to this episode. I hope I have been a fruitful host to everybody listening and to
You
Dr.
did,
Sayantan.
you did a great job actually.
Thanks a lot. And so, yep, after a long time, this is another episode of the Wimple podcast. And I hope to see you again pretty soon. And I will try to be a lot more consistent with my episodes. And we'll maybe have Dr. Sayantan uh, for a second or third or even more times on our podcast if possible.
Sure, why
S-
not?
Yep. So yeah, thank you everybody for listening. I hope you have a great day, have a great time wherever you are, and keep looking up. Thank you.
Thank you, Divyansh, for your session. It's really good, and
Thanks a lot, sir.
hopefully this will be good for the students as well.
Yep.
Okay,
Thanks a lot for coming. And yeah, yep. Any other information? Obviously, we are connected on LinkedIn. And yep. Thanks a lot for coming. And I hope to see you sometime else as well. So yeah. Bye.